Good morning, everybody. This is another colloquium for the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Professor Didier Queloz, and he will talk on the Exoplanet Revolution. Our director, Anchon Alberdi, will introduce Professor Queloz. Anchon, please.
Okay. Good morning to everybody and welcome to the Severo Ochoa IAA seminars. As director of the IAA, it is a pleasure to welcome Professor Didier Queloz to our weblogia. Didier Queloz is at the origin of the Exoplanet Revolution in astrophysics, when in 1995, during his PhD with his supervisor, they announced the first discovery of a giant planet orbiting another star outside the solar system. This seminal discovery has spawned a revolution in astronomy and kick-started the field of exoplanet research. Over the next 25 years, Didier Queloz's scientific contributions have essentially been to make progress in detection and measurement capabilities of exoplanet systems with the goal to retrieve information on their physical structure to better understand their formation and evolution by comparison with our solar system. More recently, he is directing his activity to the detection of Earth-like planets and universal life. In the course of his career, he developed astronomical equipments, new observational approaches, and detection algorithms. He participated and conducted programs leading to the detection of 100 planets, including breakthrough results. He participated to numerous documentaries, movies, articles, TV and radio interviews to share excitement and promote interest for science in general, and particularly topics about exoplanets and life in the universe. Didier Queloz is professor in astronomy at the University of Geneva, and professor of physics at the University of Cambridge. He has been jointly awarded the 2019 Nobel Prize in Physics, along with Professor James Peebles and Professor Michel Mayor. Welcome, Didier, to our institute. He will give today the talk about the Exoplanet Revolution. I will pass you the floor.
Thank you very much. Well, first, I do regret not to be with you in person to visit your beautiful country, so we have to rely on screen right now. But I hope that one day I'll be back visiting you.
I hope so.
Yeah, thank you. So, the title is Exoplanet Revolution because I think we are really experiencing a true revolution here. One way to see that is just to count the number of discovery that we have had. In the past 25 years. So there's different techniques that being used. Essentially, these techniques are not seeing the planet. There are very few planets yet for which we have a direct image, but we're using the indirect way by looking at the star and finding either whether there is a change of radial velocity in the star or if there is a transit to detect this system, this planet. So you see really the expansion of the number of planets had been detected, and we move to a stage where we don't really care about finding a new planet because there's plenty. It's more about trying to understand what are this planet, because as you will see and as you know, this planet, most of them look quite different are looking quite different from the one we have in the solar system. So we really want to get the global picture here. So that's a good idea. So let's see what we've learned. In a way, it's an extension of the work started some time ago by Copernicus that we're experiencing right now. We're trying to rescale and recenter and understand how we're fitting in the global pattern of all the planetary system in the universe. So let's start with the solar system, something we know very well. So the most relevant information that we have in our planets and we can retrieve for the planet is not only this beautiful picture and the understanding of the planet we're having. It's also the fact that some of these planets clearly have core inside of them, and the fact that they are cores, it's kind of a tricky measurements to get the core, and still a lot of debate exactly what is the nature of the core, and the case for Jupiter. But a close flyby and the multi moments of the gravity field help you to design to add constraints combined with the nature of just interior model of planet. So the fact they are core is quite an important piece of the puzzle here, because related to the core, there is all this mechanism of the buildup of the planet. So I have to spend a little bit of time on this, because this is really relevant about to understand this many other planets we have under the stars. So let's have a look first at the solar systems from above. These are a picture, in a way, that you would get if you would identify with a bright light, in that case, green for the small object in the Kuiper belt, and we have the cyan and kind of pinkish for cyan for the giant planet, and then the sun here is in red, and then you have this pinkish, which is another set of asteroids. So the reason why I show this picture is to show you the scale of the solar system, and to not to forget that the solar system is not only the inner planet and the outer giant planet, it's also a lot of other bodies that are making the global picture of the solar system. So if you want to understand the planet formation, you have to understand all of it. You cannot only be dealing with the planet. So the interesting element here is to have a look at the scale, which is about 50 AU, and to see what we have achieved quite recently at the similar scale under the stars. So you all have, bear in mind, this is where the Jupiter here. So we're all aware of this beautiful picture of HL Tau, which is exactly at the same scale that I'm showing before. So both images are put at the same scale. And I think this is a very convincing case for all of us that such a protoplanetary disk should be not very, very far from the protoplanetary disk that made the formation of the planet. So in a way, we have one of the many ways to form planet, and one of the many ways starting from basically the same kind of ingredient here. Well, this image is fascinating for many aspects. Well, first of it, I think it's an achievement. It's the technology achievements to do this kind of image with ALMA. The other interesting element, it is a very the wavelength, which is in the millimeter, is capturing the thermal emission of all the particles you see in the disk. So it's a thermal map, if you want. But when I say thermal, it's only getting an object which is about 30 to 50K here compared to the background of which is the 3K of the background of the universe here. So it's very cold compared to what you can sense as a temperature, but it's bright enough to see all this many object there. So what essentially we're seeing here is the solid object that is in the disk, and solid object is a very small fraction of the story to understand the planet formations. The solid object is the one that acts as a seed, and that's the one that you expect to be part of the core, and that's the one that are forming the planet, the inner planet there. So to understand really the process in a very simple way, how you start from this stage to end and to have a planet, you have to look at the disk in a different way. And keep in mind that most of the mass of the disk is invisible. You have almost 100 to 1,000 times more mass, which is invisible here, which is gaseous. And gaseous, most of the gas is into the hydrogen, and this gaseous, you don't see it on this picture, because it doesn't give you this thermal picture you have here. So to understand a bit more, you have to look at another disk, which is very famous, which is the Beta Peak, which in that case is seen from the edge. And we have to change a little bit the scale to pay attention. We have to expand by a factor 2. So Beta Peak is looking a little bit more extended. At least we are able to capture this. certainly for the one on the top, which is a visible image done with the Hubble Space Telescopes. So what you do see here is the disk of Beta Peak from a side, and you see the reflected light on all the solid particles you have on Beta Peak. Well, you see clearly that the disk is on the edge on. Clearly, there is no doubt about that. You can even see that there is another disk, and there is the reason why for that is you may be aware that there is a beautiful planet that has been imaged and detected on that system. That is the reason why you have this warp disk. But that's not what I want to say here. What I want you to pay attention to that is how thin is the vertical direction of the disk. And this very, narrow range or thickness is really the key to understand the planetary formations. And it's the key ingredients to understand how we ended up with having a planet there. Because if you have the very same picture of the very same object in the very same scale, but not looking in that case about the reflections, but you're looking in the millimeter range where you detect molecular transition from the CO gas, which in a way is tracing the gas that you have in the disk, you have a rather different picture here. Well, the first is much thicker. And if you really compare with the scale, the disk is less extended. So you have a much more compact disk and much more thicker. Well, the reason for that is very simple. Because it's a gas, and the gas doesn't work the same way than the gravity. You have also to sustain the pressure in the gas, the same kind of way that you explain the pressure when you go in altitude. And this is why the gas has this kind of structure. There is a self-balance mechanism which is maintaining some thickness into the gas. But the important aspect here is there is no gas beyond some distances. And the fact there is no gas is simply because this gas, in the case of the CO here, is not anymore in a gaseous form because it's cold enough to become a solid particle. And this solid particle, because it's not anymore sustained as a gas, it will collapse on the center of the midplane. And you will have something very thin. And this mechanism that is moving the gas into the solid is a very essential key ingredient into formation of the planet, because you have an enhancement of the number of solid body interacting each other because they're very close to the midplane. They're all very compact, and that's the origin of the core of the planet. So this mechanism is the reason why everybody is expecting the core of a giant planet that is later going to trap all the gas around to be located within some distance from the star. In that case, this is CO disk. So CO disk needs to be pretty cool to become solid. But if you do exactly the same with the water, and water is a bit everywhere, it's a very simple molecule that you see a bit everywhere in the universe, then it's a bit closer. It's about 5 AU. So this whole idea of the fact that you form planet at some distance come from that very point. And I doubt that we will come another way to form planet. So we have to accept that this is very likely to be the main ingredient that forms the planet. But then we're coming with a problem, because we know that a lot of the planet have been found way closer to this boundary. And when you're talking about a planet like 51 Peg-B, for example, you certainly expect this planet to be formed away and to be moved in. So the concept of the motion at the same time you're forming the planet has been one of the main revolutions that is a result of the first discoveries, is the fact that sometimes the ingredients that is at play when you form a planet, they're stronger on some system compared to other ones. Maybe because they are a different kind of disk, maybe related to the composition of the disk, the size of the disk. Maybe there is a nearby object that is going to wipe out the disk. There's plenty of good reason for this to happen, but it's certainly happening. Now, with this in mind, I know this mechanism of the formation of the planet, though we can try to understand what we have found today. So if I jump into almost today, this is the situation with all the planets that have been found on other stars, I think 2 weeks ago. Each of the point here is a planet. this planet has been displayed according to the parameter for which we have a direct measurement. So the period of the planet, the radius of the planet, the blue dots are the one detected by transit. The radius is one of the outcomes directly coming from the transit. And the red dot are the planet found by radial velocity, with, in that case, the assumption that the sin I of the angle is 1, just for the purpose of the diagram. So this two diagrams have to be seen in a stereotic way, in a way, because one tells a story, another one tells another story, but that's really the reality. And there's some of the objects for which they have both been detected by transit, and later they have had radial velocity measurements. But whatever way you just want to look at this diagram, there is a couple of striking features. Well, the first striking feature on this diagram is, and to help your eyes, I added the Earth, Venus, and Jupiter. Well, if you look on both diagrams, we have essentially not found any Earth with a similar distance and similar size or mass, whatever you like, so far. There is absolutely a lack of detection there. And if you look at the transit regime, there is essentially no Jupiter which is being found. Well, the reason why is it's not because people have not tried, because it's extremely difficult. And if you introduce the difficulty by itself of the sensitivity of what you're trying to detect, you have this kind of two lines here that give you, roughly speaking, the limitation that we are experiencing today. Well, one of them is very easy, is the vertical line on the radius, is that one, because it's just the statistics of the transit. There is so little chance, even if you have a planet, that the planet would transit because it's so far away. The alignment is so rare that I think we should give up any hope to get much more Jupiter. I mean, there are so many stars that's been studied, looked at by the transit program right now, and one of them being Kepler, and they found very little, because it's just the chance is very little. So this is completely understandable, that part. The fact that the transit has failed here, well, it was clearly capable to detect small object, because there has been detections of Earth-sized object by the space missions. It's just a matter of signal-to-noise ratio here. Is again, if you want to have a transit, if you have plenty of transit, is better, because you can combine the data together. But the transit is a very brief moment in the life of the planet. If you have a system like the Earth, it will only last for 10 hours. And for the 365 other day, nothing will happen. So it's extremely poorly efficient techniques to find this object. And that's why you have very few opportunity to have them. And if you don't have the signal-to-noise ratio to get it right in one pass, you miss. And that's what has happened here. So you can see something interesting here is if we would have if the situation in the universe would be exactly the same that in the solar system, well, I would not be talking to you right now, because essentially all the planets that we're finding would not exist. Kepler would have been a true disaster. They would not have found any planet, and it's not talking about the other missions. So the fact that we have found in transit so many planets, and the fact it has become so popular, and Kepler such a successful mission, because we had overlooked a complete new, complete part of the story here. In that sense, this is a revolution, because we had overlooked the possibility of having planet much closer. Because if you look at what we have here, we have all this hot Jupiter that is being there, and this hot Jupiter, it's one of the former categories that you also reflect here in the mass and detect by the radial velocity there. And that was the first surprise that came up. Then the second surprise here is we have this big bulk of object here that essentially doesn't exist in the solar system, that are sitting between the Earth and Neptune-ish. And they have all the names you like, super Earth, mini Neptunes, Neptunius, and mini Saturns for some of them there. So I'll come back a bit to explain a bit what we're talking here about. This population is actually the same that is being seen here in radial velocity here. The radial velocity is in a way a bit more interesting on that diagram, because you can see all this population of objects which have the mass of Jupiter, but have a longer period. So there are clearly a set of planet that seems to be like Jupiter, while the exact understanding what is the extent for which you can call it a planet, because if you move it in a too high a mass, you will hit the brown dwarf, and the exact definition between the two classes is not very clear. And there is an expect when you want to look at objects which are much farther out. Some of them have direct imaging and detections. Then you bias your observations to very young objects, for which it becomes a bit tricky in some case to get an exact mass and understanding what you're really detecting. So it's a very difficult regime, but still there is plenty of high velocity objects that clearly have a mass within the Jupiter range. Keeping in mind that most of them have an eccentric orbit. So in a way, they're not similar to our own Jupiter planet in that sense. So the other step from here, which is not something you can do by looking at this diagram, you have to rely on a very careful statistical and threshold work, which is to assess for each of these objects the kind of occurrence. If you look at the star, how likely is this going to be that you have a planet in that category? So these are the numbers that you kind of find in the literature, and not everybody agree exactly on some of them, but it gives you the ballpark idea. So clearly everybody understands that the hot Jupiter is not a very common situation. So the fact you have a Jupiter that is moving in, whatever it's by the migration or by a three-body encounter or a quasi effect, is still limited in terms of likelihood. It's only 1 to few percent. So in that sense, having 100 stars when we started the survey with Michel, it was expected that we had one of them in our sample. Actually, we had two. We had 209458 as well, but we were quicker on 51 peg. The other interesting bit is this massive populations that we called short period systems. Most of them, they come into systems. So they clearly, there seems to be massively present on stars, which has an indirect consequences is if there are so many of these, it means the solar system alike are not that common. You cannot argue that more than half of the stars have a system like our own. Clearly not, because more than half of the stars have systems that are different from our own. So, well, it doesn't preclude this system to also include a planet like the Earth, like it is, but that's clearly a different scenario, because in that case, you would have a much more planet, a much closer. Remember, and most of these planets are closer to Mercury. So they're really close. We're talking about 10 days, few days, 1 day for some of them, and shorter than 1 day for even some of them. So that's really an extreme population here, but it's fascinating populations. Well, this population is a golden mine for the transit, because since they are so short period, the likelihood of transit is very high. And that's the reason why of the high success of the transit missions. And that's the very reason to fly tests, because of this population here. Now we have then this population of Jupiter. Now there is a big uncertainty on this one, because it depends a bit of the assumption you're making, and it depends of the author and the extrapolation they're making. If you stick to a very strict regime, few Jupiter, in few AUs, you end up with a few percent, 5–10%. But if you extend it further out, then you try to connect the direct imaging with a lot of biases. So there's, the assumption you're making becomes a bit more fragile, and then the range of possibility increase, and you cannot reject a very high level of planet that will be more massive than Jupiter. When I say more, going to 5 to 10 Jupiter mass at distance further out. And when I say further out, it means 10, 20, 30, 50, 100 AU into the system. It's not something we should reject, because you've seen the size of the solar system. It's clearly 50 AU. It's something we understand. We clearly understand that the you find gas up to about 50, 60 AU. And we have to bear in mind, if the migrations, depending of the density structure of the disk, if you have more density inside in the disk, the migration goes in the other direction. So the migrations, bring only the planet inside if there is more, mass outside than inside, which is the case in most of these disks, but it may not be the case in all of them. So there's a possibility that some of the system you have just the opposite effect. Instead of moving the planet in, you would move the planet out, having a planet, quite significant planet in this distance. And that would be the kind of discovery space for the next generation of direct imaging facilities here, and I'm thinking about ELT here in that context. And also there will be interesting news coming from Gaia. Gaia will start digging into this regime here. So you see, it's a fascinating regime. We are very far having understood this diversity, but we have to acknowledge, the diversity is there, and this kind of 101 version of the planet formation I gave you before, I think provide enough room, because there is enough branching in this scenario to explain this diversity. Well, the consequence as well of that is when you're talking about a planet which has the size of the Earth, well, you can end up with a different kind of planet, because you can be talking with a planet that takes 8-9 hours to go around its stars, and in some case it's very hot, and in other case you can talking about a planet which have a different story, which that could be have different thermal story, and then it opens the possibility of a different kind of structure. I come back on the structure because you see some of the point here have red and blue as well, so it means we do have for some of the stars, we have measured for the planet the mass and the size, and then having access to density. Before doing that, I just want to explain a little bit this limit here for the radial velocity. The radial velocity technically these days has the capability to detect a planet which is not very different from the Earth. The main issue is we are so close to the noise, let's say the intrinsic structure of the dynamic of the photosphere, so that is really prevent us to easily dig out and find these planets. And just to give you a little bit of a flavor of that, so recent interesting work, a lot of these very accurate facilities now include a solar telescope, and during the day, instead of standing still, they observe the sun. And this is when you observe the sun with a very precise machine like HARPS North in that case, but that would be exactly the same. There's been other surveys being done by other programs. And what I would like you to notice is this is the radial velocity here, and essentially all the structure you see that is not related to the instrument, is really what the sun is doing. You see that the typical rotation period of the sun that create these ups and downs, but you see also the intrinsic scatter and a slightly gradual change according to the rotation period of the sun. So this is to give you a little bit of an idea of the challenge. This is 1 meter. So 1 meter is classically reached right now by any standard instrument trying to hunt for planet by radial velocity. You can have an idea what it means if you decreased it by factor 10, which is what you need when you want to find Earth, which is there. So I think the intrinsic noise of the photosphere, or the structure of the granulations and the inactivities and spots, splash, anything you can think about, is the next challenge. And there's a couple of experiments right now. One of them I'm leading, which is called terra hunting, but I don't have time right now. But we're trying to establish a new milestone here and to break this frontier of I'd call it the 1 meter per second fog from the photosphere here. Okay, so still some work to do. So you see, if you're entering into the game, if you're young, I mean, don't be shy. Don't get the feeling that because we have found so many planets, the story is told. Actually, when you look back at what we had before, and we found nothing here. So we really have to work hard, either on transit or either on that regime. On transit, Plato will push this boundary clearly, and there is a whole new generation of radial velocity machine of survey that is trying to hit hard here in these regions, and I'm hoping they will improve this, and in my lifetime. Okay, so a very fascinating diagram is when you combine the mass and the size object for which you combine both techniques. It's very efficient, whether you start radial velocity and find the transit, or most of the case you do the other way around. You have the transit and then the radial velocity. So this is a situation as if 2 weeks ago with the 1 sigma error bar and this measurements. This is log scale, the mass in Earth mass, the size in the Earth radius. So to help your eye as well, I just add a couple of emblematic planets. So Jupiter, Saturn, then we have Neptune here, and then the Earth will be here, 1, 1. Okay, to help as well, I have included on this diagram the effect, what you would expect to sit if you have the similar structure than Jupiter on this dotted line. So on the gray dotted line, it's assuming exactly the same kind of structure of Jupiter, but moving the mass, and you look what the size is doing. So you would lie along this regime here. So anything that would look, strictly speaking, like Jupiter would be around this regime. So Saturn is not very different, by the way. You notice that most of the hot Jupiter, they are above here in terms of radius. It means the density is smaller than the density of Jupiter. So we know that. It's called the inflation effect. So most of them are clearly inflated. The reason is very likely to be related to the fact they are hot Jupiter. So they are much hotter. The atmosphere is much hotter than Jupiter due to the illumination and the energy of the sun. But frankly, there is no rock solid, no physical mechanism that has been clearly identified to explain that. So it's still an open-end situation, and people are still arguing why, but that's a fact. So we have to live with that right now. We do have object that seems to match Jupiter, but most of the case, this one are not hot Jupiter. And then there's a bias here, of course, because they are transiting. Hot Jupiter, easy to get to transit, so that's why you have them there. Now, when you go down, there is something that you notice as well, is you cannot explain Neptune with a similar structure than Jupiter. Well, we know why, because in a way, Neptune is seen as a failed giant planet, in a sense that when the core was accreting a lot of gas, the gas vanished. So Neptune was too slow to accrete enough gas and to end up like Jupiter. And you still have the core, so you end up with something much denser. To help you to understand that, just draw a very hypothetical planet which would be made only of water. So essentially, you still have the hydrogen there, but you add oxygen. And it makes the planet much heavier. Then, of course, the nature of the water will be different. Inside, it will be called hot ice, but it doesn't matter here for this. What I would like to show you here is there is a whole range of planets in this regime, which is called the Neptune mass range. Some of them clearly that would fit like Jupiter and Saturn. This is why when you have a Neptune mass, you would well qualify to be what is called a mini Saturn or mini Jupiter. It doesn't change anything because you're still there. But you can also be sitting with something which is a little bit denser, with less gas, less hydrogen practically, along this kind of line. It's kind of a absolute mess. I mean, we have to just to acknowledge this, and even having some planets clearly that are more massive than Neptune here, which seems to have failed to accrete the gas as well, like this object there. It is as if you had a very bigger core, and there is a theoretical prediction that there is a maximum bigger core you can accrete, we can get with 60 Earth mass. So that's about matching here. We have not found anything here. So in a way, there is no really a planet more massive than 80-ish Earth mass that would not start accreting the gas. So it's either you reach this regime, or you stick here. So the interesting element here is when you draw the similar diagram, assuming then an Earth density. So it's strictly the Earth, 1, 1. So you increase the mass of the Earth, keeping the Earth structure as it is. You would be along this line here. Well, the Earth is essentially a planet without atmosphere. So you have a core and a mantle, and that's it. The atmosphere is absolutely, can be neglected here. It's irrelevant for that kind of modeling. It doesn't really matter. And you would lie along this line here, and I think this was interesting element that people start to realize when they were discovering this object, is there are clearly planets in this mass range that you can say few Earth mass up to few to a Neptune-ish, which is a regime that usually we call super Earth or mini Neptunes, where a planet would be more like a Neptune or more like the Earth, and we don't really know until we measure it. So I just take the example, just take 10 Earth mass here, and then you can end up along this line or that line. And if you pay attention, there has been even further studies here, and you can distinguish a kind of a gap between these two regimes here, called the Fulton Gap, which is actually telling you that you have a strong kind of binormal structure. It's either you have a planet essentially without atmosphere, because that's what it is here, or you have a planet with a thick atmosphere, in the sense that an atmosphere that will be more like an atmosphere like Neptune's. And this strong division here should be related to the formation of the planet, but having the mass doesn't tell you anything essentially here. Well, what you can learn here, it doesn't seem the Earth, the planet without atmosphere, only rocky, doesn't seem to go much beyond 10 to 20 here, and then the L bar are pretty large. So there is a kind of a limit here, and it doesn't seem that we have much planet which a significant amount of atmosphere with a mass less than 2. But this is highly, biases in a way, because all these planets have very short period and they're very hot. So if you consider just the fact that you have a hot planet, there is no way the atmosphere can just survive, just by the nature of the dynamic of the kinetic energy that you will get by the fact it's just hot. So it may not be really a real limit here, but a kind of an intrinsic limitation due to the fact we're only talking about short-period planet here, highly limited. So bear in mind. But I think this is a fascinating story because the story is rather different from the perspective of the solar system. And clearly the idea that you have a very strict dividing line between the telluric planet, the ice giants, and the giant planet is broken apart here. So that's the second aspect of the revolution. So we are seeing more the planetary formation as more as a continuum. But because of the different phases that are getting quicker, faster, more likely or less likely, you have this kind of feeling of an accumulation, so an enhancement of object at a given phase. So clearly here, which are all the planets that fail to accrete enough gas, and that's maybe why you have a lack of object in this regime, and then you find quite a lot here because you move quite rapidly from there to there, and that was the kind of this kind of difference that we see between the hot Jupiter and then the short-period systems that has been found. So, well, if you want to make a picture of that, well, essentially what is happening is this is right now the extension of the first image I show you. So early on we had only this and then that. No, we have to just add Y more. Of course, we won't have the same kind of beautiful picture, but this is all the possibilities. You certainly have massive core subgiant to explain the extension of Neptune regime beyond the Neptune. And then you have to think about all these possibilities here, whether you bring a Neptune down and you have mini Neptunes, or you can even bring a gas dwarf, and there's just a core with a lot of gas, what's called ocean planet, and then you can have what's called super Earth. It's a very big rocky with a very tiny atmosphere. So frankly, this is a hunting ground for the next 20 years. And one way to move forward here is to get a little bit obsessed by looking at the atmosphere. When I say looking at the atmosphere, it's just finding out whether there is an atmosphere. And say, is the atmosphere bigger than 100 kilometers or less? That's the first question I think you can address. One way to do that is to use a bit more carefully the transit light curve. So if you have never seen a transit light curve, so that is a beautiful transit light curve, which is now in all the textbook that has been produced from space. It's what you get when you get a space telescope and you observe like it's Kepler data. And you observe the transit, which is the time when the planet goes in front, and then the secondary eclipse or the eclipse when the planet is behind. So when you zoom in this, you see this kind of pattern here. And the reason why I insist on that is because this phase is a fascinating phase, because that's the only moment when you see only the star, because all the rest, you have the planet around as well. Whether the planet is produce a thermal flux or just a reflected flux, it's irrelevant here. You still have the planet around. But that's the very moment when the planet is behind. And then essentially, this is the star, because it is defined by the moment when the planet is behind. All the rest is the planet. So this is why, we can learn about the atmosphere of the planet, is if you can use all this feature here. So you can use this feature, well, you can have a look at that moment here, which is the planet when is what's called the day side, just about going behind the stars and being invisible. So they give you directly the amount of flux of the day side. If you see this called phase function, similar to the moon, you can derive a lot of the pattern going on and the atmospheric and dynamic of the atmosphere going on the planet. You can do even more by doing that. You can do that in many different wavelengths. And I just got a series of beautiful picture that I'm stealing to my colleagues, Vivian Parmentier, which is one of these beautiful ISS picture when you see the Earth, and in that case the Moon. And the reason why I see the Moon, because I just want to help you to understand what I mean by you can use the wavelength to tell you something about the atmosphere. This is a visible light, and you clearly see the atmosphere, the tiny bit of atmosphere of about 10 kilometers. That's the Rayleigh scattering of the blue. That's why you have the sky is blue that you see here. Well, if you do exactly the same in the 8 micron waveband, it's completely different. In that case, you see the floor of the planet. You don't see anymore this upper atmosphere. So this is the rock of the planet. It's a thermal emission from the Earth that you see here, and you use the Moon to just drive your eyes. And then you can do something else. You can look slightly at the different wavelength, not very much, 9.6 micron. 9.6 micron should ring a bell for most of you. That's the ozone. And you see the ozone is much more extended. Well, we know why, because we have an ozone layer at 20 kilometers, 22 to 50 kilometers. So, sorry, no, it's 50 kilometers. No, I think it's 20, 30 kilometers. And then it clearly makes a difference. So you can use this fact that the planet doesn't have the same size at different wavelength to actually retrieve the spectral feature in the atmosphere. And I won't talk more about that because I don't have the time, but that's the rule, hard to do that. And you can even push it and do that in a very high resolutions. And again, you can derive directly some element from the atmosphere. So that's the way to move forwards the development of the field here. Now, I want to briefly talk about a little bit the extension of this activity towards the life. And the reason why I've flipped this diagram is because this is famously known habitable zone that everybody's talking about. So I just want to, in a way, clarify what is about a habitable zone, and then maybe hoping that the community will become adult about when they're talking about habitable zone. So habitable zone means only one thing, is there is liquid water, minimum conditions. And it's assuming some atmosphere that you can play around, but that's it, nothing else, nothing more. Now, when you look at almost of the planet that has been found so far, they would not be fitting into the habitable zone. That's where lie the habitable zone in the solar system. So the trick that people are doing right now is instead of using planet, orbiting stars like solar type stars, they're trying to have a look at planet orbiting cooler stars, so-called M stars. In that case, the very same population that I've shown you before, and there is plenty of them, then is fitting into the habitable zone. So it opens a very interesting prospect to have planet with moderate temperature in the atmosphere, where you could maybe see you could maybe extrapolate the trace if you find water as a gas, that there is also liquid water on the ground. And that's all about habitable zone. And that's, I think, is good enough, having to be an interesting element to look for that. So because of this trick, and people get a bit obsessed of trying to use this element to find out whether there is water, already this first question on planet, the trick is to look for small stars. So it's a very extreme system, the TRAPPIST one. I don't want to talk too much about that, but essentially, if the star is at the very bottom of the main sequence, in that case, you can find a kind of a similar rescale versions of the solar system, but with the planetary system that would be within the orbit of 51 Peg B. Essentially, that's what it is in the TRAPPIST system. So what is fascinating with TRAPPIST is because there is a multiple planetary transiting systems, and because there is so many planets which seems to be aligned like like a piece of art, all these planets are in resonances. So you don't need radial velocity to get the mass. You can rely on the TTVs. There is a beautiful paper of Hegel revisiting, 3 years of TTVs on the TRAPPIST systems and trying to derive the mass. And we're having this very fascinating moment right now when the whole TRAPPIST system is essentially fitting within the mass radius diagram, similar to what you expect from the Earth and Venus within the L bar. Some of them are slightly off by tiny bit, but it depends the assumption you're making on the composition. So I think this is a very interesting moment because it shows that we should not be afraid that some system may look different, maybe difficult from one techniques, and they always will be sooner or later another approach. And that's a very fascinating object. So the question I would like to talk about in the last 5 minutes is, because TRAPPIST is clearly a rocky planet system, because TRAPPIST is within the habitable zone, because the TRAPPIST system is a main target for James Webb Space Telescope, and people will be looking for water. If we have water, what can we say about life? And I would just to pave the way a little bit for the discussions. And that's, I want to share with you a result of a program that I started a couple of years ago. I was frankly a little bit embarrassed, but seeing a lot of claims about life on planet that I found completely unfounded. And I've saw so many misuse of the word of habitable zone as a consequence of there's life on this planet. I decided to try to restart from the beginning and trying to understand what we're talking about when talking about life. So I went to see my colleagues, biologists, and they explained to me what is life. And in a way, that is what is life for biologists. So it's a beautiful machinery with an entity to produce, to replicate with the genomes, not too perfect, but perfect enough. Then you need some metabolism that makes the system working. And then you need to be able to produce stuff, which is the purpose of the proteins. And then you need to protect that, to have the membrane. So essentially these 4 ingredients are there, but I mean, they are beautiful ingredients. This is what life, but from an astrophysics perspective, I think it's completely irrelevant. So there's not really any useful information you can derive from that, unfortunately. So we decided to bounce back and to ask the question from the astronomy perspective is, how far could you learn something about that stuff using the tool of astronomy? So what are the tool of astronomers is to be able to do atmosphere. I mentioned that before. And there's this beautiful, I mean, multi-picture of Wiki Meadows, which I like very much to show. These are all planets that are in the habitable zone and that are displaying clear detections of water in the atmosphere or something related to water but hitting the oxygen. So the reason why I show this picture is you can well have oxygen and water in the atmosphere. It doesn't say anything about the fact that you have liquid water, even if you are within the habitable zone. Because to really understand that, you need to understand the geochemical interior of the planet, and you need to talk to geochemists. And I think this is something I start realizing, and this is why in many different places right now there is the developments of a joint activity, which is a bit different from what has been done following the Mars missions in the 70s, when you have biologists talking to astronomers, making the astrobiology. In that case, it's more geophysicists talking to astronomers, and then geophysicists talking to chemists and atmospheric chemists, and then chemists talking to biologists. And before the biologists, they're talking to a category of chemists that we call a molecular chemist. And that's what I would like to talk right now, because I think this is the way to make progress, and rather than going directly from the biology to the astronomy, which is, as we've seen in the last 40 years, and not leading to any results seriously on that topic. Now, the point I like to make is, I think what we need to understand is not to detect life, is what is the ingredients that we need to have to make life possible. It's talking about the universal building blocks of life. This is related to prebiotic chemistry. So before having life, you need some kind of prebiotic chemistry going on. And this prebiotic chemistry should be not a small detail. There should be a significant element which is making the chemistry on your planet. So we have now these 20 amino acids. Why 20? I think this is a serious clue of what is needed in terms of ingredients to produce this. So, and a couple of years ago, there has been the tiny revolutions in chemistry that have proposed for the very first time chemistry mechanism, a whole chain of reactions to produce amino acids. And what I like with this is a testable element from the astrophysics perspective. What do you need to make the amino acids? Well, if you look at the Patel paper, 2015, this paper is telling you need water. That's pretty clear. Nobody's challenging this. SO3 is a direct production for volcanic activities. So you need some volcanic activities. You need HCN. It's very little gas, actually, but it's key to make the chemistry working. And HCN, there is plenty of them on Comet. HCN is produced on Comet because when you have a C, N, and H, and under the UV radiation, you make HCN pretty easily into comets. So comet is falling onto the planet early on, produce a very nice delivery of HCN. Atmosphere doesn't need to be very special, which is good because we know when you form a planet, the atmosphere is essentially CO2. So it's not highly reduced atmosphere. So reduced means there is not much energy to make the chemistry. So the chemistry, you do it with the UV flux from the star. So that was the big change. These chemists have made the assumption that the star would be the key ingredient that make life. And that led to a paper that we did in collaboration with my colleagues, chemists, where we reproduce the star and demonstrated that indeed there is enough flux on the sun early on to produce this amino acid, and then a possible pathway for life. Amino acid is not life, but that's certainly a starting point, assuming that the life has used this 20 amino acid for a good reason. So we come up with this definition that we call a biogenesis zone with Paul, where we compare this with the habitable zone against the period and the temperature of the star. And we found out that the abiogenesis zone, which is a region where there is enough UV flux to produce this chemistry, works pretty well on planet orbiting star like the sun. But unfortunately, it doesn't work on TRAPPIST. Well, you need to argue massive flares if you want to produce enough UV flux to create that chemistry. So the interesting consequence of that, if you're right, I think the 20 amino acid that is the base of life on Earth are not possible. They were not available for life. It doesn't mean there is no life, but it certainly means life would be more difficult to explain and to find, because we don't even know how life is made in that case. At least the fact life is based on the 20 amino acid makes our work easier. So I would like to end with 2 slides here to give you this global perspective. And I think the purpose is to make the astrophysicist a bit more humble when we're going to tackle this problem of life and detecting more and more of this planet in the habitable zone. One of them is a diagram I stole from my friends, geochemists. This is the story of the Earth from a geochemical perspective, starting with this nebular phase, which is very relevant for planet formation and the business of astronomers, to a very complex interaction between the hot magma and the evolution of the atmosphere. Of course, a lot of infall from carbon-enriched asteroids. That is, it may have even completely vanished and recycled the whole planet atmosphere. And then you enhance the atmosphere by bringing the CO2, all the hot magma, the partial melting of the core. Of course, you have a lot of gas getting out of that, and you have a gradual evolutions of the atmosphere of the Earth, producing the SO2 with possibly the prebiotic happening somewhere here, and then you have life production of the oxygens and making this atmosphere like we know it today. So the reason why I show that is if you want to understand the planet, we should bear in mind this is a geophysical problem. And whatever we do with the atmosphere, we will have to bring it back into the geophysics before trying to understand life and before making any proper claim on that. And this is a kind of ongoing direction where people are moving. There will be planet detected. There will be planet on small star being measured, but we should have this in mind. Now, what about life here? So I would just share with you my perspective. I think life is a physical problem, which is in a way simple because it's just chemistry, but at the same time, there is this concept of growing complexity and aliveness. So I see the problem as a chemical reactions that takes control gradually of itself by increasing complexity. And there is a point that is to be defined, which is called the alive threshold. When you reach this point of aliveness, so the evolution takes control and you are in a biology domain with the Darwinian evolutions and all this competition. But before you reach this level, there's a lot of ingredients that needs to be put together. And this is where the fun is. If you are an astrophysicist, a geophysicist, a prebiotic chemistry, or somebody building from the biology perspective, the macromolecule, because you must reach the scale, or you must build up. And this has to match, because you cannot argue that you have such a macromolecule if you don't have the prebiotic chemistry massively going on before. You cannot argue for the prebiotic chemistry if you don't have the element which is being used by this prebiotic chemistry to make the chemistry. It's called in the dirt. And you cannot argue for the geophysical condition of the planet if you don't know what's going on in this planet. So there is a close link between these 3 domains here. And I think this is a future evolution of the questions of going for life in the universe. And I do predict that we are making a new field of research, which is not anymore astrophysics, which is not anymore geophysics, which is not anymore chemistry, which is the study of life in the universe, which is a kind of a similar new field that popped up in the 50 and 60 after discovery of DNA that created right now this grand field of research with dealing with the DNA. So I will stop you on these ideas and opinions that I share with you, and I welcome some questions. Thank you very much.
Thank you very much, Professor Queloz. And now the talk is open for questions. For doing that, please raise your hand. For raising your hand, press the button reactions, and then you will have there. And the question will be managed by Pedro Amado. So Pedro.
Yeah, we have some minutes for short talks. So if you would like to ask anything, you can do right now. Otherwise, you will miss the opportunity to ask Didier any questions. So I don't see the hands should be here in the chat in the participant view, I suppose. René?
Yes, still no questions. I'm looking in the YouTube.
Fine. I will have to go in 10 minutes. So
yeah. I would like Didier, if I have the opportunity to ask one question related to this very last transparency that you have set up. Regarding this new topic of study of life in the universe that convolves the knowledge from many different perspectives, where do you think the next breakthrough will happen in this study of life in the universe topic, either from an instrumental point of view or from the knowledge that we are deriving from all these topics?
Well, thank you for the question. So that is a bit the point of my talks. Is I don't think we can rely on a single unit here to really make significant progress, because that's a whole chain of event you have to build. So that there is a different element here that will have to be put together, and each of the sequence we need to progress. Well, first, we're missing an Earth twin. And we need absolutely having rocky planet on sun-like star inhabitable zone, for the very reason that if you want to use, if we assume that this is a true mechanism producing life, then in that case, we need this object. And we have failed. Right now, we essentially focus on them stars, and all them stars for which we find planet, even a system like TRAPPIST, according to this theory, would not be the right one. So we should be careful not to get blinded by the fact we have so many objects on them stars that to study. We should keep also the progress moving and not rejecting this, which means maybe rethinking the way we operate the surveys to find this object. That's the first element. That's what I'm doing on my hand and trying to support with the Terra hunting, which is breaking a lot of taboo in astronomy, because you need to dedicate telescopes and all this kind of stuff that people doesn't like to do that. Now, the other aspect here is, I mean, having the planet is not enough. We need to understand the atmosphere of the planet. So we should get rid of the transit in a way as a prerequisite to study the planet. Of course, we will do that for the next 20 to 30 years, because there is a series of elements like Plato and then Ariel and then all the LT, and we'll do a lot of them because that's what we have. But we have to bear in mind, for one transiting planet, you're missing 1,000 planets. So you have 999 planets you not using for one transit, because the fact that the transiting is very unlikely. And the more you want to move in the habitable zone, the more you want to move to a solar-like star, the more dramatic it becomes. So we should really think that, and there are efforts, and the Starship missions, and there is other, and LUVO, and there is LIFE experiment that is trying to project the possibility to just extract the atmospheric informations or the surface of the planet information without the need of a transiting planet. So that's for the next 50 years, and that's something which is going on from the astronomy perspective. Now, Mars missions will be an absolute breakthrough in a sense for the planetology, because we are going to bring back stuff. Well, now we have beautiful image. We have this very emotional moment where the lander went. The most emotional moment is when we're going to bring back some piece of rocks digged out along the way and being able to analyze it with a great detail and on Earth. Because there's a lot to learn here. I mean, this theory I mentioned, I mean, if you believe to that, I mean, there is a prediction. Life must have started on Mars as well, because the first billion years old was not different on Mars than on Earth. So the very similar mechanism should have happened. And then you should see some geochemical traces and these early developments of the chemistry on Mars. And even more, we're going to see maybe some early macromolecule tracing that will be imprinted in the rocks of Mars. I'm not even dreaming having detecting any life really still there, but it's already some traces here. So I think Mars will be key, and similarly challenging the theory by going to Titan on Enceladus, where you predict the formation of life completely different, because in that case you don't have the UV flux, you have a different environment. That would be really essential, because never put your egg in the same basket. So I think here that is also going to happen. I know there are plans to do that. So I think from the exploration of the planetary of our own solar systems with a specific a prospect to understand better the geochemical environment and then the prospect for life is essential, because it brings the geophysical context here. Now, of course, in the wet lab of my friend biochemist, they need to make progress. And I'm expecting one day we will hear that someone has made life in a lab. So as I said, the 20 amino acid is not life. So how do you move? Do you go from 20 amino acid to something much more evolved? But if you think that at the end, you only need something which is barely working, you don't need a full functional entity. You need something which is poorly efficient, but just a little bit working, with a little bit of way to transcribe the informations, that would work. And I know the membrane is being done. They do membranes. They assemble. There's some way to assemble proteins that is being found, and then the proto-RNA is being developed in labs. So I really expect here there will be some kind of game, where we're playing Frankenstein here, but we're making life, and we have controlled the mechanism of the sun by controlling the fusion and the fission. Well, sooner or later, we will control the mechanism of life. I don't see any reason why. The only reason that would prevent us to do that is we're going to disappear before we reach that level of knowledge, because we're crazy enough these days. But aside this reason, I don't see any reason why we will not reach that level. So I think there will be progress there. And then having progress there, people will have to think about what is the exact interaction of life with the planet. Because remember, we're never going to go there. And we have to rely on detections, except that the solar system planet. So we have to develop very sophisticated modeling that will be combining the geochemistry, the biochemistry, to try to better understand. It's going to take 100 years to get an understanding of that. But the idea that there are planets for which there are atmosphere, there is water, for which we're going to detect, maybe we're going to see some changes. We're going to see the rotation of the atmosphere. We're going to see maybe continent on some of them. It's certainly something which is within grasp for the next 100 years. And that's how I see the field evolving. That's why I think this is a new field of research, because it combines too many elements together. And I hope, and I'm trying a lot to spend my voice right now, which is hearing a bit further down than it was in the past, is to convince the funding agency to stop the silliness to divide field together. And it's extremely difficult right now to still fund these disciplines, because people, you're either on the astronomy or you are on the biology side, but you don't really fit between the two, with geophysical, astrophysics, and micromolecules building up. So this is where I see the future. So we have a glorious future, and I know the topic is very attractive for young generations. So I think our responsibility will be to make sure we pave the way and offer opportunity for these new generations to embrace this field of research. And that's what we all have to do.
Okay, thanks, Didier. Thanks also for your nice seminar. If you still have a couple of minutes, we have two questions. It has to be very short.
Yep.
Yeah. Okay, Emilio Alfaro, please go ahead with your question.
Thank you very much, Didier, for this nice talk and very inspiring talk. So the last slide was beautiful, you know, with the different contribution, with the different possible contribution all together for, you know, for knowledging something about life. My question is double. First, do you consider that life can be considered a statistical matter? So the statistical approach is something valid for knowing something else about life? And the second question is, how can we not produce artificial life in our labs with these ingredients?
Yeah. Well, I think the production of life, as I mentioned, is something that is likely to happen one day in the molecular labs, because that's what they're trying to do. I know some people are trying to do that because they're trying to assemble and to find the tricks how to, and they're much more advanced. I've just shown you the first bit, which is the productions of the amino acid, because this is, I think, quite well understood right now. But there's a lot of element going on trying to assemble the early machinery of life. Now, your question about statistics is very interesting, because I keep arguing that we should stop seeing the field of planet discovery and understanding of the planet as black and white. It will become way more statistical in the future for the very reason that it will be difficult to absolutely claim of what we're going to get. And even if the claim for having a planet like the Earth, because you're so much fighting the signal of the star, so there will be maybe some level of uncertainty. So it all depends on the Bayesian approximation, Bayesian assumption you're making of the systems, and assuming some assumption you're making, you will end up with some statistical significance of it. And we see that more and more right now. People are developing more sophisticated analysis of the discoveries because of that reasons. It's even more profound for life, because we would have just a couple of spectral feature that would be ill-defined, because that we never resolve properly this. We'll be resolving some kind of a mixture of it. So there will be different model. So depending on the assumption, you enter into a Bayesian kind of structure of a statistical element here. So altogether, that would be a gradual build-up. So I think we should get used to, as we should be as a scientist, to give up this idea of, oh, there is that star with that planet that look exactly like that because there is exactly life. This is not going to happen like that. There will be a likelihood that there is a planet according to the data, some assumption you're making in the way you treat the data. There will be a likelihood of the understanding that you will build up on the atmosphere, assuming the same, and then further on. And then gradually, when you build up the evidence, you will gradually build up more stronger element to, at the end, learn something, because at the end what we want to learn is exactly how unique we are, and that's how I see it.
And probably it's only, you know, the way we have to approach the problem in some way. No.
Sorry, I missed what you said.
No. I say that my last comment was, and probably is the only way we have to approach the problem. You know, in some way. No, it's looking for something in the, you know, in this big amount of planet we have discovering. All right, thank you very much.
Okay, thanks, Emilio. We have just one more question.
Yeah.
Oh, just one. Yeah. Adriano Campo, please go ahead. Make it short if possible. Thanks.
Thank you. Thank you very much for the great talk. So my question is, water on Earth has likely been carried in by asteroid and comet collision. So do you think that the presence of some small body belt can increase the possibility to rise life on exoplanet systems?
Well, that's a very good question. I think certainly more information you have on the system, the better you are. That's certainly true. So coming back to the water on Earth, I think this is not clear cut because according to the isotopic of the water, you would derive the origin of the water, and you would expect most of the water comes from the outside of the solar system, and this cannot be. We know that because there is no way to explain the ocean like it is today as only coming from that part of the protoplanetary disk. But certainly, I think the idea that part of the water has been recycled and comes from outside is very true. Whether you need to have a very special event coming up, whether it's something that comes gradually, I think, frankly, the water, I'm so amazed that there is still people debating on the origin of the water, but we cannot claim right now that the water is only of comet origin, because it would not work on the isotopic assumption. So the other element with water is you can look also about water on Mars, and I think will be a very extraordinary achievements to bring back water, analyze the detail of the water. Is the water the isotopic ratio of water on Mars the same that we have it on Earth? That would be really tremendous to know that. And there's a lot of debate also of the water on Jupiter, and comparing the three kinds of water. You know that the probe failed to pick up the water before reaching the layer when you had water. So I think the water is certainly an ingredient you want to use for the reason I mentioned before, because it was early on a key ingredient that can move from two states. And because of this change of state, it was certainly a key driver of formation of the planet. And then there is tons of water available then on the on asteroids. So the idea to look in detail about the water is extremely good. And having additional element about the possible asteroid structure or zodilite in a way, and if you want to call it the similar way that we have it, so some dust around leftover, would be a very interesting piece of information. And that's why we need direct imaging, because direct imaging would definitely get this result as maybe a preconditions to have a more evolved system. So yeah, so the future is so glorious on that.
Okay, thank you very much.
Okay, thanks, Adriano. I think we have to stop here. This
I'm sorry,
very interesting seminar.
I have 15 minutes to get some lunch.
Okay, so I would just want to thank you for your time, Didier, and I hope we can have you here in Granada in person soon.
Yeah, I'm sure.
Thank you. Thank you, Didier.
Have a good day. Thank you. Bye.
Thank you
Thanks
very
a lot.
much.
Thanks for the
Bye-bye.
invitation.